It took one more generation of mathematicians to get to the bottom of this. Cardon student Raphael Bombelli made some incredible insights about what's really going on here. Let's remember why Cardon was stuck. The square roots of negative numbers ask us to find a number that when multiplied by itself will yield a negative. Neither positive nor negative numbers will work. Bombelli's first big insight was simply to accept that if positive numbers won't work and negative numbers won't work, then maybe there's some other kind of number out there that will. Now, if there is some other kind of number out there, a good follow-up question is, what are we going to call it? After all, we need to use it in our equations. Bombelli's approach was a very practical one. Rather than dream up a new name and symbol, Bombelli simply let the square roots of negatives be their own thing. In the past, mathematicians would have thrown in the towel here and declared the problem impossible. But Bombelli was able to press on simply by allowing the square roots of negatives to exist. Let's take a simple example of our new numbers, the square root of -1. For being a new kind of number, it doesn't look very exciting, and might kind of seem like our old numbers. But remember, it does have the exact special property we need. When we square it, the result is negative. Further, since our number doesn't behave like a positive or a negative, it must be something new. Now, if this all seems a bit fishy to you, like a slightly too convenient algebra trick, you're in good company. In fact, it's hard to introduce imaginary numbers without them sounding like an arbitrary invention. However, before we dismiss the square root of -1 as some abstraction invented to torture students, let's review what we've learned so far. Cardon and Bombelli were genuinely stuck on a tough problem that they knew had a solution. What Bombelli was able to see is that if he extended the existing number system, as had been done so many times before, he could solve the problem. Just as people needed fractions, zero, and negative numbers to solve new problems in the past, to solve this problem, Bombelli now needed the square root of -1 to be its own brand new number. Let's make sure we're clear about what it means for the square root of -1 to be its own number. If our new number is truly a discovery and not an invention, it should behave like the other numbers we already know about. It should follow the established rules of algebra and arithmetic. And it turns out the square root of -1 does, for the most part. Just as we can split apart the root of the product of two positive numbers, we can also split apart the square roots of negatives. The square root of -25 splits into the square root of 25 times the square root of -1. This process is important because it allows us to express the root of any negative using the square root of -1. The square root of -25 becomes 5 times the square root of -1. We can use this process to expand the root of any negative number, writing it as some number we already know about times the square root of -1. Let's quickly make sure that our new numbers follow the same algebra rules as our old numbers. In algebra problems with x, only like terms can be added and subtracted. 2x plus 3x is 5x, but 2 plus 3x is just 2 plus 3x. Likewise, 2 square roots of -1 plus 3 square roots of -1 is equal to 5 square roots of -1. But 2 plus 3 square roots of -1 is just 2 plus 3 square roots of -1. Finally, unlike terms can be multiplied, just as in algebra with x. 5 times x is just 5x, and 5 times root -1 is just 5 roots of -1. Now, there are some cases where our new numbers behave a little strangely, but these can often be avoided by first separating out the square root of -1. Now that we have a grasp on how our new numbers work, we can see how they fix one of our problems from last time. We now have a strategy for dealing with the roots of negatives. We can evaluate the square root of -9 we were stuck on and obtain 3 times the square root of -1. We left off with Bombelli's discovery that if he allowed the square root of -1 to be its own number, he could solve problems that had been stumping mathematicians for decades. Despite the usefulness of his discovery, Bombelli and other mathematicians generally regarded it as a hack. After all, what could it possibly mean to take the square root of a negative number? Just like our friends zero and negative numbers before, the square root of -1 was generally regarded with suspicion because it didn't correspond to anything people could think of in the real world. For this reason, the square root of -1 was given the terrible names imaginary or impossible. A century or so later, Euler began using the symbol I to indicate the square root of -1, making the algebra less clunky. Unfortunately, the name imaginary stuck around, and that's still what we call these numbers today. In response, everything on the original number line gets the name real. When we put together a real and an imaginary number, we obtain what we today call a complex number. What is remarkable about this time period is that although imaginary and complex numbers were used in calculations and derivations, The deeper meaning behind these numbers was left undiscovered for over 200 years after Bombelli's death. Before we dive into this deeper meaning, let's think about I algebraically for a moment. If we raise I to higher and higher powers, it doesn't get bigger as other numbers would. We know I squared is -1 from the definition, and if we keep multiplying I by itself, we see a pattern that repeats every 4 multiplications, over and over and over and over. Hold on to that fact for 90 seconds. Let's return to our friend the number line. Remember that all the numbers we know about show up here, except imaginary numbers. They are nowhere to be found. If we think back to our original problem with the roots of negative numbers, we can visualize this using the number line. Remember, the issue we had was finding a number that when multiplied by itself would yield a negative. To see this more clearly, we'll use arrows instead of dots to indicate numbers. Multiplying a positive by itself maintains direction on the number line. It stays positive. If we multiply by a negative, we flip directions or rotate 180 degrees. Squaring a negative lands us in the positive numbers because we start on the left side with our first negative and rotate 180 degrees when we multiply by the second negative. So there's no way to land on a negative number when squaring. A positive squared results in a positive, and a negative squared requires starting in the negative territory, and when we multiply by the other negative, we arrive back in the positive numbers. So what we need is something in the middle, a number that when we multiply by it only rotates 90 degrees, not 180 degrees as negatives do. This is exactly what imaginary numbers do. I squared is -1, meaning that the first I puts us 90 degrees from the positive real numbers, and multiplying by I rotates us 90 degrees further, exactly where we want it to be, firmly in negative number territory. Back to that fact you were hanging on to. Since multiplying by I corresponds to one 90-degree rotation, if we place our imaginary axis at a right angle to our number line, our algebra will perfectly fit with our geometry. If we start with the real number 1 and multiply by I, algebraically we get I, which geometrically corresponds to a 90-degree rotation from 1 to I. Multiplying by I again results in I squared, which by definition is -1 and again matches a 90-degree rotation from I. As we keep raising I to higher and higher powers, we keep rotating around, with our values repeating every 4th power, just as they did algebraically. So the big insight here is that imaginary numbers do not exist apart from the real numbers, but right on top of them, hiding in a perpendicular dimension. This is the deeper meaning behind imaginary numbers. They aren't just some random extra number or hack. They are the natural extension of our number system from 1 dimension to 2. Numbers are 2-dimensional. And what's even more remarkable is that if we accept this, that numbers have a hidden dimension, we end up not only with a more complete mathematics, but with incredibly powerful tools for science and engineering.